I'm bringing the the PowerPoint up.
Uh-huh. You need, yep, it's just loading.
All right.
Uh, could you
Go back.
give a quick introduction to yourself? Let me just share with the audience. We have Jay Perry speaking with us now. Did you want to give an introduction, Bob?
Go ahead.
You probably.
Yeah, and our next speaker is Jay Perry at the Marshall Space Flight Center. He's our subject matter expert in the field of air revitalization. Jay, all yours.
Okay. Thank you, Bob. Okay. Good morning. Let's see. Do we have any time constraint? I know that you have lunch coming up next, and we're about 30 minutes behind.
Yeah. So we'll shoot for 12:15. So if you could do it in 45 minutes.
Okay.
But don't feel rushed. If there's important things you feel that you need to share with us, take your
Okay.
time with those.
All right. Sure will. Thank you. All right. Well, good morning, everyone. And I know that so far this morning you've heard quite a bit about some architectural considerations and some history. This morning, and with this presentation, will be specific to atmosphere revitalization. Many times it's also known as air revitalization, but I like to distinguish a little bit between air, which we breathe here on Earth, and an atmosphere in a spacecraft or a space habitat, which can indeed be rather unique to that vehicle or habitat. So in that regard, we tend to call it an atmosphere because it can operate at different pressures, different oxygen concentrations as a result of operating at lower pressures. And then in of itself, it can have its own characteristics from a microclimate standpoint. So in that regard, I tend to, technically like to use the word atmosphere in place of air. And so let's move on to this presentation with our contents. First off, again, even though you've heard a bit of history, I also want to look ahead a little bit. But in looking ahead, we also need to understand how atmosphere revitalization has been accomplished on past vehicles and on the station presently. So in that regard, we'll take a short look back, at the same time thinking about how we're trying within NASA to think about how we take the station and apply it to the future. We'll go over some atmosphere revitalization design basics, some top-level considerations. Also go through some functional process design considerations. So we do have, from my chemical engineering background, I like to do things with process flow diagrams and process and instrumentation diagrams. So I won't disappoint you there, so that we do have some flow diagrams in the presentation. And then we'll wrap up. The last chart on this presentation does include a listing of recommended reading and also some web links to some documents that are available through the NASA Technical Reports server if you do the search on the document number. It should bring that up, and then you'll be able to download those in PDF. So moving forward with our agenda here, let's start first off the future and our little look back. What we're trying to do in the future. First off, we're going to kind of reverse things. One of the things that within NASA that we're being tasked to do is to critically look at the life support systems on board the International Space Station and think about how they might apply to our future mission and vehicle architectures. One of the, some of the things that we're really being specifically asked to do is to really pay a lot of attention to improving the reliability and maintainability characteristics of the equipment that's used on board the station. Obviously, when we go outside of low Earth orbit, we are going to have to eliminate this ground-based logistics resupply model. There may be other types of resupply models that come into play, Those may be in situ resource utilization based. They may be based on some type of ferry flight vehicle that just goes in a circle between Earth and wherever the habitat might reside. We don't exactly have all the details on that yet, but we've got to definitely start cutting our ties to a ground-based logistics model. We also need to innovate when needed. A lot of our base process technologies and some of the equipment technical solutions such as fans and blowers and valves and sensors and things of that nature we need to operate the equipment. Some of those already are termed rather robust. However, they may have some technical weakness that hinges into a reliability or a maintainability issue. In those cases, we want to go in and say, well, what is out there that's brand new or emerging, where a new innovation may actually help us to close these technical gaps on the reliability and maintainability aspects. As well, we rely a lot on physical adsorbents and chemical adsorbents and various oxidation and reduction catalysts to do atmosphere revitalization. With a lot of the press push toward environmental regulation, emissions control in the chemical industry, all the work going on now as far as carbon sequestration and being able and having capabilities to capture carbon dioxide from industrial and other processes. There are these technological improvements happening in the realm of catalysts and adsorbent materials, and so there are improvements there that NASA can benefit from. And so we look at these as technological improvements that may fit within the envelope of our existing equipment. And we also want to look at the system infrastructure. This is how all the different components are tied together. Obviously the station, with all the equipment mounted in racks, a future vehicle may not have a rack equipment mounted type architecture. So exactly how does this equipment need to be packaged? What makes sense as far as putting the functional components together to yield the most volume efficient, mass efficient, and thermodynamically efficient system that we can possibly come up with? It's obvious that with our experience with station that we can do a bit better as far as those aspects going forward. Also, too, we have to pay attention to maximizing the commonality across all the missions and the vehicles. Going forward, we don't want to be going and redesigning a life support system or with every time that a new vehicle comes along. We want to be able to take a lot of our basic atmosphere revitalization processing components and be able to apply them from vehicle to vehicle and mission to mission. It's just a matter of maybe how they might be placed within that vehicle that's the most, as far as that infrastructure that may be more customized from vehicle to vehicle. But we want to have components that can be used so we're not having to go back and redevelop and do new development every time a new vehicle or a new mission comes toward us. We're also looking to do a lot of work to mature the emerging process technologies as far as our technological improvements and in looking at system infrastructure aspects as well. Again, we want to be able to go in by doing this early technological maturation, reduce our technical risk and cost to the future flight programs. The less developmental work as far as technology maturation that a flight program has to do, that means that schedule can be compressed, and then there's less technical risk and less cost because that work has already been done. I think that this next item, developing the modular resource recovery technologies, is rather critical. And the thing is, it can be either in or out of the functional need, depending on whether you need to get more of the oxygen back from the carbon dioxide. In other words, do that closed loop life support system. to what extent does closure have to be met? Does it need to be, is 65% okay, or do we need to go to 75 or 90% or greater than 95%? Again, there will be mission specifics and other types of exploration specific, exactly what we're doing on a surface, whether we're going to use in situ resource utilization or not, and some other considerations come into play as to whether we would have to close the loop to a high percentage. Given that, we want these loop closure technologies, the carbon dioxide reduction specifically, to be more modular, so we can add them on to a core process design whenever we might need to. And finally here, what we're all about, I think more than anything else within NASA, is promoting cooperation, and that's cooperation across the agency, cooperation with our international partners, commercial space enterprises, and of course academia, like we're doing right now. Okay, we'll move on to the next, to take a brief look back. Actually, we'll go back through, we're getting to the point here of what is atmosphere revitalization, and I think then we do take our look back. First off, this is our, what we affectionately call our bubble chart, showing all the major functions of the life support system and their possible interactions. Just about every function that we have in a life support system interacts to an extent with each other. The bubbles that are outlined in red are key to the atmosphere revitalization system, encompassing carbon dioxide removal, carbon dioxide reduction, trace contaminant control, and oxygen generation, and total oxygen, nitrogen, or atmospheric gas control, I think if we would call that generically. And we also have, a lot of times include in air quality. When you think about air quality in a building or a home, down here on Earth, we also do think about temperature and humidity. When we get into designing HVAC systems for commercial residential buildings, temperature, humidity, and carbon dioxide are three of the main considerations as far as the indoor air quality is concerned. Of course, we do hear a whole lot more about the trace components, the trace chemicals that can build up from all of the upholstery and other materials that are used in a commercial or residential structure. Well, it's the same type of thing with a spacecraft. I always tend to look at, or we consider a spacecraft, we think about a tight building and tight building syndrome. A spacecraft many times is viewed as the ultimate in tight building design. Obviously, our entire intent of an atmosphere revitalization system or subsystem is first off to keep the crew healthy and alive. At the same time, we have to provide a living environment that avoids the onset of sick building syndrome symptoms. So to accomplish that, we have to pay attention to all of these different functions.
Can I ask you a question about that? My
Yes.
understanding is that the sick building syndrome, that there's a number of phenomena, like one is mold, right? Black mold or things that are hidden behind panels that builds up. Another is asbestos, of course, which I'm assuming is not an issue here. Is this primarily a mold issue, or I heard stories that Mir at the end of its life was pretty, that it had a biofilm coating on the walls and was quite unpleasant. Is it primarily a mold issue?
Actually, no. On the station, for instance, we do employ HEPA-rated filtration. And some of the post-flight has indicated some mold spores in the pleats of the HEPA filters on their return. For the most part, that issue is fairly well controlled, primarily because the humidity level in the cabin is fairly low, between about 35 and 45% relative humidity. So part of the issue that gets into the mold and the mildew aspect is also controlling the relative humidity. Keeping it below 60% is pretty key to avoiding a mold or mildew bloom. Now, even on the station, there are some areas that we've heard anecdotally where the crew decided to set up a showering station in one of the modules, and they were hanging damp towels and other, and so that became an area of localized high humidity constantly. And you can imagine if you say here, living here in North Alabama, where it can get really, really humid, and after a while, mold and mildew can grow everywhere. Well, if you go and have a situation like that, you can induce a localized area where you could have a mold and mildew problem. You're going back to Mir. There were a lot of anecdotal reports about fungal mold growth, etc. Now, like Mir, Mir did not employ a HEPA-rated filtration system. They have a different level of filtration. It is not HEPA-rated, and for that reason, obviously they were not taking out a lot of the microbial load when they filter for the particulates. Their focus has been a little bit more on protecting the equipment in that regard. And to be fair, when we had shorter duration flights with the shuttle and Space Lab and such, those filters on board those vehicles are not HEPA rated either.
Can I ask a quick question?
Mm-hmm.
Can you clarify what a HEPA filter is, or what makes it unique?
Yeah, a HEPA filter is the HEPA rating, high efficiency particulate air, is what the acronym stands for. The acronym may also stand for high efficiency particulate arrestants. There are several definitions of HEPA as far as the acronym. The technical specification, it is a specific percentage removal efficiency, for a size range of particulate matter. For the HEPA, the filter is rated to be 99.97% efficient to remove particles that are 0.3 microns or micrometers in diameter. And then there is a special set of ASTM test standards and ASHRAE test standards that are used to generate particles to test the filter media, and then in that test, the media itself becomes rated as HEPA by virtue of passing that particular test. So that's the short definition of HEPA for you.
Thank you.
Welcome. Okay. So I guess, so as well, you were talking about whether it was the situation is having to do with mold and fungal growth or other microbial load in the cabin. Obviously, when we have people on board and they've been living in their homes and they bring their clothing, I think a lot of the crew's clothing for station at one time resided in their homes. Even when we did some debris assessments for Space Lab and such, and looking at that post-flight, it was rather interesting that we would see things such as dog and cat hair in that debris. So obviously, anytime we take human beings and put them in a habitat, even if this is a very pristine habitat that's been built under highly clean conditions where everybody's wearing their clean room bunny suits and everything like that, Well, the crew members haven't been in clean room bunny suits or anything like that, or away from their families and their pets and everything for long enough to completely remove all contamination of their life here on Earth. And so they do take some of that with them, and it does get there. And so anything that we, as the crew members, when we go into these vehicles, we're going to take some of ourselves with us, and that includes our whatever microbial load that's associated with our environment here on the ground. It was also interesting too with Space Lab. We would also see parts of palmetto bugs in the debris as well. Obviously all the clean rooms, the roaches and the palmetto bugs can get into anything, and so we would find leg parts and wing parts and all sorts of things like that too. So with all of our efforts, the roaches surviving since the days of the dinosaurs, they're obviously going to go to space with us maybe too. So that's something to consider.
That's a little worrisome for planetary protection, isn't it? Like if we're gonna bring things back the other direction one day.
Mm-hmm. Yes, I think that it does harken back to I guess the story in the movie Andromeda Strain, where some things did come back from outer space and they weren't too good for us down here on Earth. Likewise, we might contaminate the other way, so we have to be aware all the way around. I believe, and the experience so far has indicated that there's no 100% absolute cure to that outbound contamination or inbound contamination. Something is going to go out and then come back, very likely. Okay, and I guess adding on to the question about the microbial and fungal load, the other aspects of that are, of course, the carbon dioxide and the trace chemical, what we call trace contaminants many times. Just like in indoor air, and you hear a lot about indoor air quality, dealing with trace volatile organic compounds, or VOCs, build up. Unlike on the ground, where you can open your windows and doors, and the doors on a building are opening and closing, and then there's a certain percentage of fresh air makeup being brought into the building to help dilute built-up contamination. In the spacecraft, we don't get to dilute very much. We don't want to dilute much because that means taking more atmospheric gases with us, or finding a source of which to make the atmospheric gases at whatever exploration site that we might visit. So the exposure to part per million levels of these volatile organic compounds as a whole can precipitate a variety of sick building syndrome symptoms, especially when you overlay that with carbon dioxide and also the particulate load that we've just been talking about. So a lot of that plays hand in hand. As well, if the temperature is not comfortable, if it seems a bit muggy or humid in the cabin, we can get into the other problems about mold and fungal growth if we get above 60% relative humidity, or if we have localized areas where there's condensation on the surface. We definitely don't want to have surface condensation. We don't want to have the humidity going higher than, really in a way we don't want it to go higher than 50%, just to give us some room to maneuver in that regard. So it all plays together toward that, making sure that we're not going to build a vehicle that results in a crew that starts exhibiting sick building syndrome symptoms. If they're not feeling well, they can't perform at their best, and they're having to perform at their best all the time. Okay. Any more questions on this chart before we move to one that gives us a bit more of a functional summary? I'll move to the next chart now. This is and this is more traditional. I understand too. What you're doing with your effort is to come up with a lot of really neat, out there ideas. But at the same time, this is how, just to let you know how, in a way, in the past, especially going into the space station, how we grouped the different functions. And you see here, toward the middle, we have a column called Control Internal CO2 and Contaminants. And at the bottom, the Atmosphere Revitalization subsystem is responsible for that. So each one of these columns is a subsystem of the life support system on board station. This is how we approached it, by trying to group and categorize these different subfunctions as a subsystem, and then ultimately as the system. So if we go outward from, say, atmosphere revitalization, we also have to provide the water, we have to be able to support the spacewalking activities, we have to be able to respond to various emergency conditions and condition the atmosphere, and then control the pressure. Broadly, though, if you look at it, atmosphere revitalization, it could be argued, would also encompass some aspects of conditioning the atmosphere, controlling the atmospheric pressure, as well as the CO2 and the contaminants, and in a way having some degree of support, of provision to support the spacewalking activities, and also maybe have some type of allowance within this subsystem design that would be a design margin or a functional margin that would allow some type of response to help clean up after an emergency condition where the atmosphere might get contaminated. Maybe some dust is brought in from outside the vehicle with a surface exploration activity, and there's been a lot of talk about that problem that occurred during Apollo. Can we get to the point where surface dust from a surface exploration will not intrude into the cabin when we've got crew members going in and out fairly frequently? Probably not. They're going to bring something in with them, or there are going to be pathways that get in, regardless of how tight we try to make that, and how much effort we try to expend to try to make sure that it doesn't happen. The inevitable will happen. Dust can be quite tricky, and it can get into all sorts of places, particularly when it may have charges and we're in low gravity conditions and such, and it's going to behave and remain suspended in the air for a longer period of time. That raises, and that's just an example of how we may have to have additional particulate filtration capabilities and functionality beyond what we already use right now on station. Move on now, and this is where we get back to our history, and there's a progression here, and then to a degree a partial progression and then a little bit of a regression in how we approached doing the atmosphere revitalization systems. Starting with, and you look at Mercury, Gemini, Apollo, they were rather similar with one another as far as how we approached and I'm going to focus on the carbon dioxide removal and the trace contaminant removal. And across the board, granular lithium hydroxide to react with the carbon dioxide to remove it, and then using activated carbons to remove the trace volatile organic compounds has been very common. As we moved into Skylab with the longer duration missions, a regenerable process, a two-bed process that used molecular sieves to remove the carbon dioxide was used. That allowed for the longer duration. They didn't have to store a lot of expendable lithium hydroxide on board. But trace contaminants, again, were removed using activated carbon. It is the go-to physical adsorbent media to remove these organic compounds from the cabin. The reason I said that we go through a progression there is that with Skylab, that was a bit of a first to use a regenerable process to remove the CO2. But when we got back to the shuttle, the mission durations were a couple of weeks, so we start going back and looking at what was used for the earlier space flight missions, And so we go back to using the lithium hydroxide to remove the carbon dioxide. Space Lab also used lithium hydroxide canisters that were derived from the shuttle program. So they used the common canisters. So there was commonality between those two parts of the Space Lab module and the shuttle orbiter itself. And so we also removed trace contaminants, again with activated carbon, but there was also the introduction in shuttle of a carbon monoxide oxidation catalyst. And this is a platinum catalyst that oxidizes the carbon monoxide to CO2 at cabin temperature conditions or room conditions. Now, with the International Space Station being continuously operated, there was the idea of needing to go back to the regenerable approaches, and as well the introduction of potential capability to support carbon dioxide reduction. With carbon dioxide reduction, what that does is that it allows less water to be brought on board, since we electrolyze water to produce the oxygen on station. And so the water feed to the electrolyzer is very critical for providing the oxygen. So if we're able to recover water from the CO2 and the residual hydrogen from that electrolyzer by a reduction process, then we don't have to launch as much water in the end. And so that's our whole idea, the whole approach of why we want to have CO2 reduction. Now again, too, on the CO2 removal, the CO2 removal for station is derived from Skylab. The difference is that the zeolite material, the two zeolite materials are contained in separate beds physically, where the drying part of the bed, the part that removes the water before the bed that removes the CO2, that water is recovered and sent back to the cabin for ultimate recovery. So again, we don't want that water to be lost overboard. At the same time, the water competes for the absorption sites with the CO2 on that particular bed. So we do have to provide a very dry airstream to effectively remove the CO2 with that type of zeolite material. So it's functional in a couple of ways. Now with trace contaminants for station, we continued with activated carbons that had a heritage all the way back through the shuttle and Skylab days, but we also introduced a high temperature or a thermal catalytic oxidation reactor on board the station. And so that's where and that thermal catalytic reactor really harkens back to automotive catalytic converter technology from around the 1970s. So we're really in many respects on station. Our core process technologies in many regards really go back to about the mid-1970s as far as their origin and their heritage. So they're well characterized, well understood. The things that are very unique, of course, are how these zeolite materials and catalysts and all are packaged, and as far as the equipment that's customized to fit in the space station racks. And that's where we get into a lot of the new parts of our equipment as we do all that packaging and build the actual equipment to fit into the vehicle. Okay. Now, these are photographs of the equipment on board the station. The right-hand photograph is the atmosphere revitalization subsystem rack. The equipment extended out is the carbon dioxide removal assembly. On the left-hand side, where you see this rather large gray circle, in that upper quadrant is the trace contaminant control subassembly. And then the white box below that is our major constituent analyzer, which is a mass spectrometer that monitors the major oxygen, nitrogen, and carbon dioxide concentrations in the cabin. And to the left is our oxygen generation system rack. That contains the oxygen generator, which is a water electrolysis unit. And then in the upper left-hand part, you see an empty space. Well, that empty space now contains a carbon dioxide reduction unit that uses the Sabatier reaction that reacts hydrogen and carbon dioxide to produce water and a methane byproduct. And now the methane byproduct is vented overboard instead of venting the CO2 and the hydrogen itself, which would mean a net loss of water. So we're actually now, closing the loop more so than we did in the past. And our challenge that's been presented to us from our headquarters customers are all these items here in the center that we want to do, and we've touched on those earlier in the presentation. So, with that background, looking to our future and such, and some dates, let's go through a few design basics. This is where we get into some requirements and considerations for the design. Our basic requirements span the cabin pressure, carbon dioxide, oxygen partial pressures, our water vapor or humidity level, whichever we want to call it, our trace chemical contaminant levels, the particulate matter, and then the microbial load. This is rather simplified. I provide here for you the range of the standard that we were trying to meet, or the range that we're trying to operate within. And these are taken from station documentation. And then we have our design points. We've got to, say for total pressure, one of our design points is that we want to limit the leakage, outward. So the vehicle, the habitat has to be fairly leak tight because whatever we leak overboard, we've got to, provide some resupply for that. The carbon dioxide range of generation per person per day, so the kilograms per P-day is kilograms per person day, as noted in the note at the bottom of the table. But of course, that means that, and then on average, it's about a kilogram. But of course, there's a period of time where the crew members are sleeping, then they're under normal activity levels, and then they've got higher activity levels when they have exercise periods, and so that's going to be variable throughout the day. And so we do have to accommodate the dynamics of that variation. The same can be said about the oxygen partial pressure. There's a range of oxygen consumption by human beings, but in a daily average. Yet, of course, again, based on activity level, we have to accommodate the dynamics. The same is also true for the water vapor. As we exhale, as we sweat, we produce a certain amount of metabolic water per day, and there's a range of that based on activity level, and then there's, of course, a daily average. And again, we have to, the systems have to be able to be set up so they can accommodate those daily dynamics. Our trace contaminants, the toxicologists within NASA work closely with the National Research Council Committee on Toxicology to set what are called spacecraft maximum allowable concentrations, and that's one of those fun acronyms here. So these SMACs, and again that's a spacecraft maximum allowable concentration, are documented and developed by the NASA toxicologists, and there's that document there, the JSC 20584 document that contains that information. At the end of the presentation, there's also a web link to information about those maximum allowable concentrations. And I do believe, too, that the design point here, which is the human metabolic load and the load of volatile organic compounds coming from the equipment via a process called off-gassing, that's provided in a conference paper that was presented at an international conference on environmental systems in 2009. I do believe that paper was provided to put on your website back about a week or so ago. Particulates, anytime you have people inside, they're going to, slough off skin cells and hair and clothing fibers and so forth. these are generated at a particular rate according to their activity level. Here we're talking about 10 to the 9th particles per person per day. A lot of particles, and across quite a range. And then, of course, microbes. Again, because we are human and we do have some of these microbes that hitch a ride on us permanently. Anytime that we're sloughing off skin cells and hair and whatever comes off of our clothing with our activity, there are microbes that come off. And the acronym CFU stands for Colony Forming Unit. Okay. Those are our basic requirements. When we deal with an atmosphere revitalization system, it looks like I've got about 5 more minutes here. Try to work through here. We've only got a few more slides to go. We do have a variety of sources and sinks where the cabin loads can range from all sorts of things, from the crew to payloads and experiments used on board, the microbes. Anytime we're exchanging crews, there might be some type of contingency event. We may have cargo type processes going on with the station. We bring cargo vehicles with new equipment all the time. And every time one of those comes up, well, they're going to bring their own unique load of potential contaminants whenever the cargo comes up. And then we have our control processes, and this is the equipment that acts on these loads to provide that acceptably clean cabin environment. And I always try to call, cabin air quality is like hitting a target. And when we're designing, this is our bullseye chart where we operate within these atmosphere quality standards. That includes the CO2 concentration requirements, the organic compound concentration requirements, or otherwise the SMACs. And then we have to go through and we have to build a vehicle. We have to design a mission architecture. We have to account for everything that's going to happen. And then all of these different parameters may interact with one another. And ultimately, they may interact in a way that ultimately may affect the cabin air quality. And so we can do a whole lot of things. Well, how is when we talk about all that, well, we have to operate within the air quality standard envelope, but then we have to manufacture the vehicle and build it and select materials that are minimal in their off-gassing, and hopefully they're not going to get brittle over time and have particles slough off of them. We have to have the systems that are require few resources and fit in our mission operations concept and fit in our logistics and maintainability concepts. And all of these things ultimately go toward this center objective of our good cabin air quality. And so our design approach, and being chemical engineering and background, I always talk about unit operations. And that means just taking things and breaking them down into their basic functions. What we really have here, as far as unit operations that we use, we're either separating things or having reactions. And so we use a lot of different types of separations techniques, ranging from physical adsorption and absorption to filtration. And then we've got various reactions, chemical absorptions, oxidation reduction reactions, and even electrochemical reactions. The types of things that we accomplish with the unit operations: we dry gases, we purify them by removing all the CO2, the trace compounds, and the particles. We handle it, so we may be taking gases, atmospheric gases, and storing them or conditioning them for their water content or their pressure. And then we would produce gases, for instance, with the electrolyzing water to produce the oxygen to breathe. We may also be doing atmospheric gas production to refill tanks to use in the spacewalk, the backpacks. And also we may process materials at a location. If we've got water ice somewhere, we may try to extract that and then be able to get our atmospheric gases from there. That's our good summary there. And then to go that route, we talked about some of our strategic improvements. This is mainly a listing here, and since we're pretty much running out of time, and I know you're getting hungry, these are areas that we are trying to really key upon as far as strategic improvements over where we stand today with our space station designs. Our station design concept takes all of these different core processes, and then they're hooked together functionally in this way. So all of the way that these all the arrows go here between ventilation system where we remove the particles and circulate everything around, and we monitor the cabin, we provide the gases. The crew has water and food, and then they consume oxygen and produce water and CO2 as well. And then we process through our CO2 removal, our trace contaminant, our reduction, and our oxygen generation processes. So this is a real just simplified representation of what the station system looks like for atmosphere revitalization. We want to go even further in developing things. This is where we take things and break it down into a functional trade space, and then look at different technological options for providing the function. And this is where we are today within NASA as far as where we're looking at different strategic things to either augment or replace process technologies with station to make them more reliable and robust. Again, I offer that for you to be able to study this in more detail on your own. Now, when we look at the testing, this is even more detail, getting down to how everything is hooked up. And we do have ground-based functional equipment. There are photographs here of the functional equipment and how they're set up. We have trace contaminant control here in the middle, CO2 removal, carbon dioxide reduction, oxygen generation, and major constituent monitoring represented here. And this is a process flow diagram with a little bit more detail showing how all these different subcomponents within these equipment may look and how they flow together. And then we're looking at, well, how might we take some of these components and hook them in differently, and then incorporate some new process technologies. For instance, here is a different type of catalytic reactor design to remove the trace contaminants that we've been working on for a while with a small company in Connecticut. And so we're looking at adding that into our mix, and then maybe combining the different functional components a little differently, taking our trace contaminant beds and then putting them in different locations to take advantage of where a blower is located as opposed to it having its own dedicated blower. And then adding more capability on to the end here to process the methane that our reduction reactor produces and get more of the hydrogen back, which means less water having to be trucked up to the station or to wherever the destination may be.
Jay, a quick question. When you're hooking up these process units together, and you have to make a sizing decision, right? How much can they process per unit time? And right. Since I think you alluded to it a little bit, but if the system is going to work in steady state all the time, that's nice because you can just size things in the right proportions. But what if there's large variations in different species being produced and consumed? So the crew works out, right. All the crew works out at the same time like crazy. You're going to have a lot of CO2 produced that provides right. a spike in the system. So how do you deal with these with the synchronization issues among the process units?
Right. Yeah, and that's a good point because in taking, say, for instance, we'll focus on the CO2 removal unit. Effectively, with an atmosphere revitalization subsystem, that function tends to be the core function. Carbon dioxide and be able to handle the range of concentration or load dynamic that can result we would like to be able to control the concentration to fairly steady level. But that means that we have to accommodate that range of CO2 production down to very low levels while the crew is sleeping to very high levels when they're exercising. And so what we do is that, for instance, we can either use feedback control, where we take a measurement of the CO2 and then say, well, you know what, it looks like there's a trend up, so we need this blower right here to run a little faster to accommodate that. What we try to do, though, is if we are going to have things operate more simply, we may have this blower at a fixed speed, but we have to have it at a fixed speed that accommodates the upper end of the load dynamic, which means we have to accommodate the exercise. So we do look at that whole range and then make sure that the design itself is able to accommodate that dynamic, and with particular emphasis on the high end of that dynamic. And so then not only that, we may even throw in some engineering design margins, the old little additional fudge factors that engineers like to throw on their designs just to make sure. Mm-hmm. So and some of our design margins can range anywhere from 10 to 20%.
Mm. And I assume that you're also working with buffers, like intermediate buffers or storage, or not so much?
Where we need to, for instance, this process for CO2 is cyclic in nature. So the CO2 that we would feed to our reduction process, there is a buffer storage tank in between to dampen out pressure cycling that happens with the regeneration process of the CO2 removal unit. So there's a compressor that then feeds into a tank, and then that buffers out the pressure cycling. And that means we can get a steady CO2 feed into our Sabatier CO2 removal unit here. The Sabatier likes to have steady feed, whereas here it's a cyclic process that sees a lot of pressure cycling. So obviously the Sabatier is not going to be too happy with that. So we do in places incorporate buffer tanks and things of that nature to take care of that.
Thanks, Jay.
So that's where we do have to understand these different stages, and that's why I look at it as a unit operation approach. We have to understand what this reactor here likes. We have to understand the process conditions that happen with the CO2 removal process, etc. Otherwise, when we put them together, they probably wouldn't work too well together. So there is a look at it that maybe we may be optimized more in one area and sub-optimized in others, just because we have to take all that into account. Okay, so I think we're getting closer to lunch, and so we're right here on our concluding remarks here. What we try to do and have been trying to work toward overall, with our technology development and extending station out of low Earth orbit, is to look, really consider this functional and unit operation driven approach, focusing in on strengths and weaknesses that we've observed and documented with the station system design, and then trying to make sure that our future designs are even more robust than what we've got with station. Obviously, when we've got a lot of experience with different core process technologies, we want to use those where we can. Especially if we're not looking at issues of commercial obsolescence with our adsorbent materials or catalysts. We do run into that problem over time, and then of course we've got to have design modularity so we can go across all these different vehicle and mission architectures that seem to be in play at the present time. And again, too, our last here is a list of different reference sources that you would be suggested for atmosphere revitalization. Most of these that are conference papers, I do believe, were sent out to put on your website. And then there are others here that that can be acquired from the NASA Technical Report Server. Some of those documents are very, very large. For instance, the Bioastronautics Data Book, the last one, is about a 32 megabyte file. But you can go to the that link, which will bring up a search box. And if you type in, for instance, on that last one, SP-3006 in the search box, and then click the search, it'll bring up a link that then you can go to that PDF document and download it. That's all I have for today, and
I want to thank you, Jay. That was excellent, and I really appreciate the reports you sent. And we do have the documents online, and we look forward to interacting with you as the teachers have more questions, and
sure.
Look forward for your guidance. Thank you very much.
You're welcome.